All right, good afternoon. We are back. All right, let's see what we got here. Hold on, setting things up. All right, how's everyone doing? Most of you I saw in the past few hours. All right, well, any questions? Looks like most people turned in their programming assignments, so I'll get those graded this weekend. Any questions on the homework?
Python down by 0k. Python is ahead. 13k.
That's my poll watcher. All right, no questions on the homework? How many people have finished the homework? How many people have tried the homework? Cool. All right, so for this homework, I said in the beginning of the course that for homeworks I would usually grade one problem, maybe more. I've been grading most of the problems up to this point. For this one, I'll probably grade just one or two problems, but I will pick, problems ahead of time to grade. So you really want to work on all of them, and I'll grade one or two of them, and then we'll talk about it. But you want to make sure that you know how to do all of them or most of them. And my hope was that if there were ones that you were stuck on, we could talk about those in class today. But and then I have office hours from 2 to 3, so that's another option. Other than that, good luck with the homework, and we'll see how it plays out. So, all right, let's go ahead and talk about the sum rule. So this is a continuation of the subject of counting. And we played with the product rule on Wednesday. Remember, the product rule said if you could do something as a succession of tasks, then the number of ways to do that procedure is the product of the number of ways to do each of those steps. All right, so you've got some procedure P, which you can do as task T1, followed by T2, and then T3 and T4. Then the number of ways to do P equals the product of N1, N2, N3, N4, where Ni equals the number of ways to do subtask Ti. That's the product rule. All right. The sum rule is the following. You have some procedure P, which can be done by completing either T1 or T2 or T3 or T4, for example, just 4 tasks. You have a procedure which can be done by completing either T1 or T2 or T3 or T4. Then the number of ways to perform that procedure P is the sum of the number of ways to perform each of those subtasks. And there's a throwback to Engineering 250 here, right? Here the procedure is done by doing T1 and then T2 and then T3 and then T4. This is a conjunction. You have to do all 4 of those, conjunction and product. Here you can do any of them. It's a disjunction, it's an or, disjunction, sum, right? Addition. So this idea of ands being like products, you know, like sum of products, and ors being a sum, like the sum part of sum of products, that plays out in here also, okay? This is one of these things that we see, the more different things we study, we see these themes popping up again and again and again. The idea of anding being somehow related to multiplication, and oring being something like addition, that's something that just keeps popping up. And so here's another example of it. Alright, so sum rule, if you can complete a procedure by doing any of a number of tasks, the number of ways to do the procedure is the sum of the number of ways to do each task. So let's play with some examples of this. So, choose a student or a teacher to send to a conference. And let's say there's 25 students and 3 teachers. How many different choices could you make? Well, you can complete this task by either choosing a student, we'll call that task T1, or choosing a teacher, T2. You don't have to do both, you just have to do one of those. Well, the number of ways you can choose a student, there's 25 students, there's 25 ways you can complete that task. There's 3 teachers, the number of ways you can choose a teacher, there's 3 ways to do that. And so the total number of ways is the sum, which is 28. Now that's kind of a silly example because, you know, you could just say, well, there's 28 people to choose from, how many ways can we choose? Well, it's obviously just 28, right? But we're using this sum rule underneath. Now, if our task was to send a student and a teacher, that's a product rule, because first you have to choose a student and then you have to choose a teacher. 25 ways to do the first task, 3 to do the second. That would leave you 75 possibilities for how to complete that procedure. Alright, so that would be a product rule. If you're only picking either a teacher or a student, that's a sum rule. Alright, if you're going to a restaurant and with your meal you get to choose a soup or a salad, and there's 3 kinds of soup and there's 5 kinds of salad, then you have a total of 8 ways that you can choose this side to go along with your meal. Now, if your salad, you get to pick from 2 types of lettuce, 3 toppings, and 5 dressings, right? That's a product rule. Because you can take this task of choosing a salad and break it into a succession of 3 tasks. Well, first I'll choose the dressing, and then I'll choose my topping, and then I'll choose what type of lettuce I want. And assuming you only have one, choice from each of these, that's 2 times 3 times 5. That's 60 or 30 salads you can choose from. Alright, that's really all there is to the sum rule. And so a lot of times we use combinations of these rules. So for example, how many variable names are there? In this peculiar language where your variable has to be 1 or 2 characters, and your first character has to be a letter, and your second character can be a letter, a digit, or an underscore. Not to be confused with a Smiley face. So the task of forming a variable can be described as a pair of options. So the task of forming a variable, we can do either a 1-character variable or a 2-character variable. So if we know how many 1-character variables there are and how many 2-character variables, we can add those together, find the total number of variables that are possible. Well, how do we find how many 1-character variables? Well, that's, arguably it's a product rule or some rule, but a single character variable has to be a character, which means it has to be a letter. There's only 26 of those. But for a 2-character variable, this is a product rule. What are the 2 tasks we use to create a 2-character variable? First, pick the first character, and then pick the second character. Well, how many ways can we pick the first character? Well, the first character has to be a letter. So there's 26 ways to choose that first character, 26 ways to complete the first task. The second character, well, this can be a letter or a digit or an underscore. Technically, that's a sum rule, right? So we could say, well, you could either pick a letter or a digit or an underscore. And there's 26 ways to pick a letter. There's 10 ways to pick a digit. There's 1 way to pick an underscore. So add those together. That's 37. But most of us wouldn't break that down to a sum rule. We just say you've got 36 characters to choose from, 37 characters to choose from. So there's 37 ways to complete that task. However you get there, the answer here is there's 37 ways to do that. And so the number of ways that you can pick a 2-character variable is 26 times 37. So whatever that turns out to be. So 962 ways to complete this option. 26 ways to complete that option. Some rule says total number of ways to do our original task is the sum of those. So 962 plus 26, that's 988 possible variable names. All right, questions on that? That usually feels pretty straightforward. All right, so let's talk about subtraction. And this is another version of the principle of inclusion-exclusion, which we looked at in set theory. Principle of inclusion-exclusion related to the number of things in a set. And it said if you have 2 sets, A1 and A2, the number of things in their union is something like the sum of the number of things in each set. But anything that's found in both sets is going to get counted twice in this sum. And we have to subtract off that overcounting. Well, how many things do we overcount? Exactly the number of things that are in common to both sets. In other words, the cardinality of the intersection of those sets. So this is for finite sets. And so principle of inclusion-exclusion says the number of things in this set, sum of the number of things in each set, minus the size of the overlap. Well, we can do this with counting arguments. So let me give you a quirky example from computer science that illustrates this idea. So here's a question. How many 8-bit numbers are there how many 8-bit numbers start with a 1 or end with 2 zeros? So start, I'm going to say that's most significant bit, so we'll be big endian. And end, I'm going to mean least significant bit. So how many 8-bit numbers either start with a 1 or end with 2 zeros? Well, let's form a set A1 equals the set of 8-bit numbers that start with a 1. So these numbers look like 1 followed by 7 bits. So how many such numbers are there in this set? How many 8-bit numbers can we find in this particular form? That's non-rhetorical, so I'll sit here and eat my lunch. There we go. Okay, 2 to the 7th or 2 to the 8th divided by 2. Both correct answers. This is a 7-bit number. We can fill in these 7 bits any way we want. So how many 7-bit numbers are there? 128. Alright, good. Now let's make a set A2 equals 8-bit numbers ending with 00. So those are numbers that look like this. How many of those numbers do we have? So how many 8-bit numbers end with 00? And if you look at it like this, we can fill out these 6 bits any way that we want. Yes, perfect. So this is a 6-bit number. How many 6-bit numbers are there? 2 to the 6th. That's 64. Now if we add these together, we're going to get 192. But that's more than the number of 8-bit numbers in this group, because there are some numbers that are going to be in both A1 and A2. In other words, there's something in the intersection. There are numbers that begin with a 1 and end with 00. So we need to know how many things are in the intersection. Well, if something belongs to A1, it starts with a 1. And if it also belongs to A2, it ends with a 0. And so how many numbers are there in this form? Two to the 5th. What we're doing is we're trying to find the number of 8-bit numbers that belong to both of these sets, A1 and A2. And any 5-bit number will give us a number that starts with a 1 and ends with 2 zeros. And there's 32 of those, 2 to the 5th. So if we want to know how many 8-bit numbers are there that start with a 1 or end with a 0, we're looking for the number of things that are in either set A1 or set A2. And principle of inclusion-exclusion tells us this is equal to the number of things in set 1 plus the number of things in set 2 minus the number of things in the overlap. And so this gives us 160. So that's the principle of inclusion-exclusion. And this is like those problems about, you know, Some people go to see Star Wars, some people go to see Lord of the Rings, and some people go to see both. And you want to know how many people went to the movies. And you can't just add up the number of people who saw each movie, because you have to take off the double counting for the people who saw both. Let's see, so we looked for the things in the intersection because both had some 8-bit numbers that were shared. Yep, exactly. Exactly. For example, the number 1 followed by all zeros would be counted here, and it would be counted again here. So we take off one of those. All right, cool. All right, next topic. So this is something called the Pigeonhole Principle. I actually just got to use this last night. So what is the Pigeonhole Principle? What's a pigeonhole? See if I can find you a picture. Alright, there's a reasonable picture of a pigeonhole. You know, it's a box with compartments in it that pigeons hang out in. Right? So why do people talk about this? So people have used pigeons for all sorts of things. People use pigeons for conveying messages across town in the past. Because pigeons can be trained, and they can be taught to home and return, and they can carry small parcels, like a small message rolled up and tied to one of their feet. And so these pigeons, you know, they hang out in these boxes. When we talk about pigeonholes, we're going to assume that each one of these boxes can hold a pigeon. Doesn't have to. The box could be empty, but it can't hold more than one pigeon. Your grandma used to race pigeons. Wow, that's pretty cool. Race flying ones or running ones? Because now I'm picturing drone races. Flying ones, wow. That would be interesting to see. That's really cool. So each box can hold a pigeon, but no box can hold more than one. They're not allowed to share. Okay? But a box could be empty also. All right? So we're going to play with putting things in boxes and counting them, and we're going to be able to do some really interesting calculations with that simple operation. So here's the formal statement of the Pigeonhole Principle. So Pigeonhole Principle. This is the other PHP. So if k is a positive integer, so it's bigger than 1, and k plus 1 objects are placed into k containers, then at least one container contains 2 or more objects. In other words, if you had k pigeonholes and you had k plus 1 pigeons, and they all tried to go into a hole, there'd be at least one pigeonhole with more than one pigeon in it. Okay, that's the formal statement of the Pigeonhole Principle. So if you have k objects and k containers, it's possible that, you know, you're going to end up with, let's say k equals 5, and you have k containers, and let's say your objects are 1, 2, 3, 4, 5. it's possible to put your objects into containers such that each container has only one thing inside. It's also possible, you know, that you might put 3 of them in one container, 2 of them in another container, and have 3 containers with nothing inside. Okay. But if you have more than k objects, if you have 6 objects, no matter how you distribute those among these containers, you're going to have at least one container with at least 2 objects in it. And that's kind of obvious, right? Because if we don't want to double up, well, we could put one here, and one there, and one there, and one there, and one there, and then where is our 6th object going to go? Wherever we put it, there's going to be 2 objects in that container. So k plus 1 objects, k containers, you're going to have at least one container where you've doubled up. Okay, that's the whole statement of the pigeonhole principle. I always want to put a D in pigeon, but all right, so what do we do with this? For example, in a room with 27 people, at least 2 have the same first initial. This is assuming your names are made up of letters from the alphabet A through Z. If there's 27 people, at least 2 people in the room have the same first initial. And how do we get that from the pigeonhole principle? Well, we usually imagine these containers. And in this case, I'm going to have 26 containers. I'm going to label them A through Z. So I have 26 containers. And I'm going to put each person into one of these containers based on the first initial of their name. So I take the first person, they're Bob, so I put them in here, and I put the second person, and they're Charlene, and I put them in here, and the next person is Zog, and I put them in here, and I'm going to do this for all 27 people in the room. Well, I have k plus 1 people being placed into k containers. Pigeonhole principle says at least one container has at least 2 objects. Whichever container has at least 2 objects, those 2 people in this container have the same first name, in particular, or the same first initial, the letter B. So this is one of these things that's kind of, you know, intuitively clear to us, but when we're asked to actually show this and to use the pigeonhole principle, it can be kind of weird to say, you know, well, this is obvious, you know, if there's 27 people, they're going to double up somewhere, right? So what we want to do is think about how do we take this formal statement of this principle and apply it to a situation. And, you know, if this was a math class, we would get, you know, very verbose with all kinds of definitions and Greek letters probably and things like that. We don't have to do that, okay? But I want you to think about how this principle applies to these problems that we're going to work on and that you'll see in homework next week. And usually it's imagining some sort of set of containers and then placing objects into those containers according to some rule. And the whole trick is kind of figuring out what should your containers be and what's the rule for placing people or objects into those containers. And then you just sort of whack it with the pigeonhole principle and your answer falls out. Okay, so it's a little like induction that way. All right. So here's an example. You have a quiz. It's worth 20 points, which means your score can be anywhere from 0 to 20. So there's 21 possible grades. 0, 1, 2, 3 up through 20. If there's 22 people in the class, at least 2 students got the same grade. So if you have a homework set or a quiz and the maximum possible score is 20, there's 21 possible grades. If you have 22 students, absolutely guaranteed at least 2 students got the same grade. Right? That's just the pigeonhole principle. Now it's possible every student got the same grade. Maybe everybody got a 20 on the quiz. That's okay. That doesn't violate the pigeonhole principle because you have at least one grade that was earned by 2 or more students. Right? So you have at least one container containing at least 2 people. We haven't violated the pigeonhole principle. All it says at least one container containing 2 or more objects. But no matter what those grades end up being, it's not possible that every one of those students got a distinct grade different from every other student's. And certainly, if there are 30 people in the class, we know this is still absolutely true because we can just pick any 22 of those 30 people, and we know that at least 2 of those 22 got the same grade. Now things may get even more duplicated because we also have 8 additional students, right? But, you know, the pigeonhole principle talks about k containers and k plus 1 objects. But if you have more than k plus 1 objects, right, this result is still certainly going to be true because you can just sort of pick the first k plus 1, any k plus 1, and that will cause this result to be true. And then when you take the remaining objects and you put them into bins, that's not going to change this result, right? It may simply make more containers have 2 or more objects. So this really works for, you know, k plus 1 or more objects, right? Or anything more than k objects. All right, but there is a generalized pigeonhole principle. And this one is a little different than just adding more people. So the generalized pigeonhole principle says given n objects and k containers, at least one box will contain at least ceiling of n over k objects. And we need to talk about what this symbology means. This is called the ceiling of x. Okay, so what is the ceiling of x? This is, let me see if I can get this right the first try. I got a 50-50 chance. This is the smallest integer bigger than or equal to x. So we're not rounding down, we're not exactly rounding up. Okay, this is a slightly different operation. The ceiling of x is the smallest integer bigger than or equal to x. So for example, the ceiling of 2.1, what's the smallest integer bigger than or equal to 2? It's 3. What's the ceiling of 2.9? Smallest integer bigger than or equal to 2.9? That's also 3. Ceiling of 2.999, Smallest integer bigger than or equal to 2.999, that's also 3. The ceiling of 3, what's the smallest integer bigger than or equal to 3? That's also 3. But the ceiling of 3.00001, just something slightly bigger than 3, that's going to be a 4. Because that's the smallest integer bigger than or equal to this. 3 is an integer, but it's not bigger than this, right? 4 is the smallest integer bigger than that. So ceiling says, you know, start at your current number. If it's an integer, just use that number. Otherwise, go up until you get to an integer. That's the value of the ceiling. All right. So, given n objects and k containers, at least one container, one box will contain at least ceiling of n over k objects. Okay, so why is this called the generalized pigeonhole principle? Well, suppose we're given k plus 1 objects and k containers. The generalized pigeonhole principle says at least one container contains at least k plus 1 over k ceiling objects. Well, this is the ceiling of 1 plus 1 over k, which is a number slightly bigger than 1. This will turn out to be equal to 2. So if you apply the generalized pigeonhole principle to k plus 1 objects and k containers, you get the specific pigeonhole principle. So this is a particular instance of the generalized principle. But this is a little more useful sometimes. So for example, 100 people in a room. How many are guaranteed to have the same first initial? And this is language you'll see a lot around pigeonhole principle problems. How many are guaranteed, or how many can you guarantee will have the same first initial? We don't know the names of these people, so we don't know exactly how many people have the same first initial, because it could be a convention of the, my name starts with X club, and all 100 people might have the same first initial X, right? But we can make a guarantee that there will be at least a certain number of people who have the same first initial, and this comes out of the generalized pigeonhole principle. So what do? We make 26 containers, we label them A through Z, we take each party member, and we put them into one of these boxes based on their first initial. So now we have n equals 100, 100 objects or people going into k equals 26 containers, and at least one container will have ceiling 100 over 26 objects or people in it. Well, 100 over 26 is 3 point something, and the ceiling of 3 point something is 4. So at least 4 people at that party will have the same first initial. Alright, is this making sense? Alright, so let's look at applications of this. So we looked at a few simple examples with grades and first initials, or 8 people in the room, at least 2 of them were born the same day of the week. Because there's 7 days of the week. We have 23 people in our Zoom session right now. How many of them share the same birthday of the week? Well, 23 over 7. Take the ceiling. That's 3 point something. So at least 4 of the people in our Zoom room right now were born on the same day of the week, which is kind of cool. I was born on a Friday. Does everybody know what day they were born on? It's a good thing to know. All right, let's look at some other applications of this. Oh, but you know what time you were born? Interesting. So yeah, we could all have been born at a different hour because there's only 23 of us. And we got a Sunday, cool. Tuesday, Tuesday, Tuesday. Oh, we got 3 Tuesdays already. See, Pigeonhole Principle works. Yep, there's our 4 Tuesdays. 5 Tuesdays. Wednesday. Another Sunday, cool. Yeah, that worked out really well. It would have totally freaked me out if it didn't work. We'd have to like call the course over or something. So let's look at some strange applications, right? Kind of along the floor of the area of tiling floors with induction, or throwing pies at people. So let's look at a unusual theorem. Every positive integer has some multiple, right? Something we can multiply that integer by has some multiple consisting of only zeros and ones. So that's a weird little result. Turn down my poll watcher. Every positive integer has some multiple consisting of only zeros and ones. Okay, well let's see if this is true. So the number 1, well that's just a 1, so we're done with that. The number 2, if I multiply by 5, that can be written as a 1 followed by a 0. So that takes care of the number 2. What about 3? Is there a multiple of 3 that can be written as just a succession of 1s and 0s in any order? What do you think? I'll cheat on some scrap paper. 3 times 37 is 111. So that works. 4 times 25 is 100. 5 times 2 is 10. What about 6? Is there a multiple of 6 that can be written as just 1s and 0s? I'll let you play around with that one for a minute. I'll cheat on my calculator over here on the side. So I knew 111 would be a multiple of 3 because the digits add up to 3. So if I had a even multiple, there we go, 1110. So that's 6 times 185. Right, and you can get that by taking, you know, this number, which was a multiple of 3, and multiplying by an even number, like 10, and so you get 1110. Nice, awesome. So the theorem is we can do this for any positive integer. Well, it's not obvious to me, at least, you know, how we might do that. It's not even obvious to me how to do this in general for any particular number. Like, 23, right? What's the multiple of 23 that can be written with just ones and zeros? I have no idea. Nonetheless, it's really straightforward to, well, it's fairly straightforward to prove this using the pigeonhole principle. All right, so let's do a proof of this. My camera is getting really laggy. In fact, I think my camera has crashed. Oh, bummer. Alright, let me restart my cameras. Let's see how this works. That did not work. I'm gonna have to reboot my machine this weekend. Hopefully I still have audio, but I'm having issues with my video. Well, alright, hold on. I gotta do some deeper debugging. You don't mind if I write upside down, right? That won't be confusing for anybody. All right. So if you can still hear me, let me know. Okay, you can hear me because you just responded to that. All right, cool. Yeah, my bus is a little overloaded. My system's been up for a while, but I've been running this Java program since September 23rd, and I think there's probably a leak somewhere, and I need to break down and reboot. So probably by Monday. All right, so you know it's going to be a good proof, right, when you have to work this hard for it. So let's prove this idea that for every positive integer there is a multiple which can be written as a combination of just ones and zeros. All right, so let's start off, you know, given a positive integer n, consider the following n plus 1 numbers. One, 11, 111, 1111. Right, up to and including a succession of n plus 1 ones. So we have a single one, 2 ones, 3 ones, 4 ones, up to and including n plus 1 ones. These are not binary, okay? These are just numbers that happen to contain just the digit 1, okay? There's n plus 1 numbers, okay? Make n containers based on congruence modulo n. So n's a positive integer. We can form congruence classes where we can say, you know, anything congruent to 0 goes in here, anything congruent to 1, congruent to 2, congruent to 3, and congruent to n minus 1. And there's at most n different things that you might be congruent to modulo n. Right? We worked pretty hard to state that a few weeks ago. So, you know, when you divide by n, you get a remainder somewhere between 0 and n minus 1. All right. So we have a total of what? We have n containers. And we have n plus 1 objects. We're going to take each of these objects and we're going to place it into one of these containers based on what it's congruent to modulo n. All right. So, you know, 1 is congruent to 1, and if we're trying to find, you know, let's say we're trying to find the product of 7. So 11 is congruent to 4, so I'll put it in the 4 container, and 111 is congruent to whatever it's congruent to. I'll put it in that container. And I'll take all n plus 1 objects, put them into this n containers. Okay, what does the pigeonhole principle tell us? At least one container has 2 objects in it. Well, let's call those objects, you know, A and B. Well, if both of those objects are in the same container, what does that mean? It means A is congruent to B modulo n. All right, I'm going to assume A is bigger than B, right? And this is where we can say assume without loss of generality, because all I'm doing is saying take any 2 objects from, you know, whatever container has at least 2 things, and let's just pick 2 of them out and call them A and B. Well, I know they're not equal to each other because these are all different numbers. So I'm just going to call the larger one A and the smaller one B. So this doesn't restrict our choice at all. So A is going to be bigger than B. Well, I know two things. First of all, I know that A is congruent to B, right? Which means that A minus B is congruent to 0, modulo n, which means n divides A minus B. In other words, if I take A and subtract B, it's a multiple of n. Well, what do these numbers look like? A is the larger number, so it's a bunch of ones like that, and B is a smaller number, so it's a smaller number of ones, and if I subtract, what am I going to get? I'm going to get a bunch of ones followed by a bunch of zeros. Right? So this is A minus B, and we know from construction that this number is a multiple of n. And that's the proof of our theorem. For that given number n, here's a thing consisting of only ones and zeros, which is a multiple of n. And that proves it. So this is you know, taking this pigeonhole principle that seems fairly obvious, but using it in a very kind of sneaky way, right, where we containerize based on modulo class, and using that to come up with this weird result that we can write multiples of any number as ones and zeros. So let's just try this with 7, just to kind of see how this works. And I don't honestly remember what multiple of 7 can be written as ones and zeros. Actually, I just remembered. But let's try this. N equals 7. So I'm going to write my 7 modulo classes. And I'm going to take the following numbers. And I'm going to try to find what each of those is congruent to modulo 7. So I'll pull up my pocket calculator. So, well, 1 is easy, right? 1 is just congruent to 1. 11 is congruent to 4. 111 so 111 divided by 7, well, that's a multiple of 7. So there's 111. 1111. This was why I stopped using cheese. So, well, that's also congruent to 0. And so I can actually stop right here. But, you know, if this had turned out to be congruent to something else, somewhere after I went through all n plus 1 of these patterns of successive ones, I would have found, you know, some place where this doubled up. Actually, this is why I don't use cheese anymore, because it loves stealing focus. Alright, but I used the wrong binary calculator. So 111 divided by 7 is 15.857, so So 111 is congruent to 6. And then 1111, that's 0.71428. So that's congruent to 5. So here's what I've got so far. And then 5 ones divided by 7, that's 0.2857. 1, 4 times 7, that's congruent to 2. And then 6 ones divided by 7, that divides evenly. So that's congruent to 0. So here's what I've got so far now. And then we need to do 7 ones and 8 ones. So that's 0.142857. That's going to be congruent to 1. And now we can stop. Because this number with 7 ones is in the same bucket as bucket as just plain 1. Right? So I found 2 of these patterns that are congruent to each other. Right? I had to go through almost all 8 numbers, but Pigeonhole Principle kicked in early. Well, so this tells me that 1 is congruent to 7 ones, which means their difference is congruent to 0 mod 7. And their difference looks like that. That's got the required form of containing only 1s and 0s. And if I do 1, 1, 1, 1, 1, 1, 0 divided by 7, that's a perfect multiple. So this, I think, is a cool proposition, right? And there's nothing in the proof that really tells us, you know, how to find explicitly what that multiple is that can be written as only 1s and 0s. But it does guarantee that such a multiple exists, and it gives us a procedure we can go through where we actually go ahead and we make our containers and we use the Pigeonhole Principle and go ahead and drop things in, and by working through the steps of the proof we can actually get to, you know, an example of the statement of the proof, which is there's a pattern of 1s and 0s that's a multiple of n, 7 in this case. So that's kind of a quirky pigeonhole proof, and a lot of these proofs are kind of slightly bizarre like that, which is kind of fun. All right. Let's do one more of these. So given n plus 1 positive integers, each less than or equal to 2 times n, one must divide another. So pick any positive integer n, and pick n plus 1 positive integers less than or equal to 2n. At least one will be a multiple of another. Okay, so for example, n equals 6. So pick 7 positive integers less than or equal to 12. The claim is at least one will be a multiple of the other. Alright, well, let's try this. We can't pick 1 because everything's a multiple of 1. We can pick 2 as long as we don't pick any other even numbers. So we'll pick 2. We'll pick 3. We can't pick 4 because that's a multiple of 2. We could pick 5. We can't pick 6 because that's even. We could pick 7. Primes are pretty safe. Can't pick 8. We also can't pick 9 because that's a multiple of 3. Or 10. We could pick 11. We can't pick 12 because that's a multiple of 2. So we managed to pick 5 positive integers, but if we get to 6 positive integers, one's guaranteed to be a multiple of the other. And if we had started with 3, then we could pick 4 and 5 and 7, and we can't do 8 because that's a multiple. We can't do 9, we can't do 10, we could do 11. Well, again, we ran out of options. We only had 5. If we started with 4, we could do 5, we could do 6, we could do 7. We can't do 8, we can do 9. We can't do 10, we could do 11. That was better. We got 6 numbers, no one of which is a multiple of the other. But this statement is that it's impossible to find 7 integers without one being a multiple of another. And this can be shown with the pigeonhole principle also. All right, so let me sketch a proof for you. Let's not get too bogged down in the fine details of this. But let me give you an idea how we turn this into a pigeonhole principle problem. So, so call your integers a1, a2, an plus 1. So these are the n plus 1 integers where none is a multiple of the other. Okay? This is going to be a proof by contradiction. All right, so we can write each number ai as 2 raised to some number times q sub I, where q sub I is odd. In other words, for each number, let's factor out all of the 2's. Okay, and just write it as a power of 2 times some odd number. All right, so a1 equals 2 raised to, let's just call it I1 times Q1. A2 is 2 to the I2 Q2. A3 is 2 to the I3 Q3. And an plus 1 is 2 to the in plus 1 times qn plus 1. Okay, if we look at all of these q sub I, these are each odd, and they're each less than 2 to the n. Because each of these a's themselves is less than 2 to the n. Less than or equal to, but 2 to the n is even. So each of these is an odd number less than 2 to the n. Well, how many odd numbers are there? And each of these is positive. So how many positive odd ints are less than, we can say less than or equal to 2 to the n. And this is another counting argument, and we can come up with an answer and prove it by induction, but let's just look at some examples. If n equals 1, how many odd integers are there less than or equal to 2? There's only 1. If n equals 2, how many odd integers are there less than or equal to 4? Well, 1 and 3. There's 2. If n equals 5, how many odd integers are there less than or equal to 10? 1, 3, 5, 7, 9. There's 5. And so the pattern seems to be that there are always n odd integers less than or equal to 2 to the n. And that is in fact true. And like I say, we could do an inductive argument to prove that from a base case workup and so on. Well, so now we have n plus 1 odd integers, and there's only n unique odd integers less than or equal to 2 to the n. Throw that into the pigeonhole principle, right? Make n containers for each of the possible n odd integers, and place each of your q's into one of those containers based on its value. At least one container will have at least 2 objects, which means at least 2 of these are the same. So there's at least 2 distinct qi, comma qj that are the same. And so this is where we could get very deep mathematically, but I'll just wave my hands at it, right? A sub I is 2 to the, 2 to the something times qi. A sub j is 2 to something else times qj, right? But qi and qj are the same thing. So this is a power of 2 times some number. This is a different power of 2 times that same number. That's enough to see that one of these is a multiple of another. For example, if this was 2 to the 5th times 17, and this was 2 to the 8th times 17, right? This is just 2 to the 3rd times that. So you have to do some argument about, you know, assuming which one is larger and then do a rule of exponents, but that's the guts of the proof right there, is break these things out into odd numbers multiplied by powers of 2. And two of these numbers, at least two of these numbers, will be just different powers of 2 multiplied by the same odd number. And those two things, one of them will be a multiple of the other. All right, questions on that? All right, I'm going to let you out a few minutes early today because it's Friday and I need to wrap up some stuff, and it's Friday. And I want to move on to talking about permutations and combinations after this, but that's a whole subject in itself and I don't really want to get started on that. So we'll call it quits for today. Have a good rest of the day, good weekend. And we will hit combinations and permutations on Monday and then build up from there. All right, thank you. Have a good weekend. Talk to you later.